All right, we'll get this thing started. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover the secure and reliable firmware updates with wolfBoot, presented by Wolf SSL software engineer Daniele Lacamera. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have any questions, please use the Q&A box, and after the presentation, Daniela will answer any questions. As always, all of our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from Wolf SSL, follow us on Twitter, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to reach out to us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of Wolf SSL. Today, Wolf SSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. Wolf SSL consists of 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including Wolf Crypt with DO178 support, FIPS certification, and FIPS ready offerings. At MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers, and JSSE support, and commercial support for curl, and our newest product offering, Wolf HSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'd like to turn it over to Daniela to talk about secure and reliable firmware updates with wolfBoot.
Thank you, Emma, and welcome everyone to this webinar. And I'd like to start indeed from our product offering. It's a quick overview of all the software components that we have created and maintain and distribute. And today we're going to focus on wolfBoot, which is our secure bootloader mostly. And this is due to the fact that we are talking about our secure boot and firmware updates today. And wolfBoot is, in fact, as we will see, the main building block for our proposed solution. So our starting point, so it's we talk about IoT security, and IoT security is not something that's static and that we can guarantee once we put the device out there. But devices need to keep being updated, and all the connected devices that are exposed to attacks need to be to public network. They need to be aware of the attacks that can happen, especially due to vulnerabilities that are outside of the embedded system owner's control. So, for instance, the components, third-party components that you assume as secure the moment they are distributed, but they can come up with vulnerabilities later on during the lifetime of the product itself. Our approach at Wolf SSL is that vulnerabilities are fixed fast, and within 36 hours from the report, we're able to prepare a new release. So whenever we discover a new vulnerability, there is an emergency procedure that allows us to basically release a new version that fixes those vulnerabilities. And of course, the problem there is how we're going to distribute those vulnerabilities for devices that are already on the field. Is there a standard way to implement firmware updates? That was the question that we asked ourselves about 6 years ago. And when we looked into that, we saw that IETF was working already on an internet draft at the time, which was called the Firmware Update Architecture for Internet of Things. That's exactly what we were looking for. This document later on became an RFC 1919, later in April 21. And it gives a number of requirements for creating a secure bootloader. First of all, the secure bootloader should be capable of authenticating a firmware image using a public key algorithm, and then a number of other things that are also regarding security, safety, rather than security, as we will see later. It's just small parser or agnostic to how firmware images are distributed, because this is a task that's dedicated to the application of the OS that's getting staged later on. But most important, this document sets the guideline for authenticating firmware using standard crypto algorithms. And on top of that, we wanted to write our secure bootloader because a lot of our customers, we noticed that they were using our crypto library to provide a custom solution for their own embedded system. But writing a secure bootloader from scratch, as we also experienced ourselves, is a complex thing to do. It might be small in size, but it needs to take into account several aspects, including reliability of a very critical component in your system, and for instance, robustness to power failure, because if something gets interrupted in the very early boot stages, something goes wrong, your devices can be bricked. So in order to provide a complete bootloading solution, even if it's small in size, sometimes we overlook the questions about time to market and things like testing corner cases, negative testing of all the things that can go wrong during a firmware update. So the same way, you shouldn't write something that should be a commodity like a real-time OS or a TCP/IP stack or a TLS, because we already provide one. The same way, you should consider using a bootloader solution that's been there for a while and that's been tested for all the use cases, and it is very robust and reliable. We would see it's used on many verticals. Our secure bootloader had some additional project goals. We started from 32-bit microcontrollers. Later on, we moved to porting wolfBoot to several different architectures, as we will see. There is one mechanism based on SHA to verify the integrity of the system, as well as a public key-based firmware authentication to verify that the signature comes from one of the authorized private keys that are allowed to distribute firmware to the system. And besides that, we also want to provide a full environment to support reliable firmware updates, which are independent from the update transport mechanism as the RFC mandate. And falling back to a previous version when everything is fine from the cryptography point of view, but maybe the firmware contains a bug and was accidentally sent to the field. And if you don't reach a specific point in the code, wolfBoot will be able to roll back to the previous working version. So that's how wolfBoot was born about 6 years ago as the universal bootloader for all embedded systems. It's designed for the IoT, as we saw, but it's ported to many different architectures, which nowadays include also Intel x86 64-bit as a BIOS replacement for mission-critical projects which cannot rely on existing stages that are not authenticated. So this is a port that has required a different level of interaction with the machine as well. So it's very complex, but still uses the same design. Different sets of machines. As you see, we also support RISC-V, PowerPC, and the NSSLX architecture. wolfBoot is OS agnostic, so we can boot any type of OS virtually on any type of machine. It can be integrated in your existing chain of trust if you already have an infrastructure that foresee several several stages. You can integrate wolfBoot into that. It performs firmware authentication at boot time, and supports different algorithms, including post-quantum algorithms, as we will see. It supports secure elements as well as TPM devices, and it's safety-oriented, as we'll also mention later. We do support optional encryption for firmware updates, as long as the firmware updates are not on a device that requires execution in place, of course, for obvious limitations. It's actively supported and maintained, as all our products. There's an entire team working full-time on new features, bug fixes, and improvements, and also providing support up to 24/7. It is portable. We reduce the hardware-specific functions to just a group of 6 functions that are mandatory to reduce target-specific code to the minimum. So it is relatively easy to port to a new platform that's not already supported, as long as it's within the supported architectures. And it supports SPI and external flash memory devices on several kinds of targets. As usual, all our code is distributed also on GitHub with a GPL version. In this case, it's GPL v3 for wolfBoot. So how it works with key management: the key pair is generated once. The key pair, the private key, is never distributed to your embedded systems. It's used to sign the firmware packages, basically, and never leaves the development or the deploy infrastructure. So the public key instead is stored on the target, as we will see. And there is limited support for revocation this time. Depends on, in fact, how immutable your key store is. But there is a possibility to upload update a version of the bootloader that can update itself. We distribute sign tool and key generation tool together with wolfBoot, and those are portable and can be compiled for Windows, Linux, and Mac. And this is responsible for creating a manifest header that's used for transmitting metadata to wolfBoot, such as the information about versions or timestamp, and it also includes, of course, the signature, which is the part that's validated, that allows to validating the authenticity of the image itself. The firmware version is also part of the verified payload, so the version cannot be altered, and that allows us to put in place a protection mechanism that won't allow to roll back to a previous version. And the only requirement here is that wolfBoot relies on a trust anchor to embed the public keys into its code, or to store them somewhere in the system in a way that can be retrieved at runtime to verify the signature of the images that needs to be validated. What's the trust anchor? This is described in this RFC here, and it represents basically a public key. So the trust anchor needs to live in the system within a specific storage position. That's a trust anchor store, and that's only requirement is to be write protected, basically. So if a public key gets read out by an attacker, that doesn't pose any risk for the authenticity of the firmware that's running on that device, or any other devices that are sharing the same public key. The only requirement is that this public key should not be modified by unauthorized users, so it should resist modifications. So by default, wolfBoot, when you download it, compile it, it will embed the public key in the wolfBoot binary itself, so within its code. And this usually is okay as long as you're relying on a fresh write protection that's provided usually by the chip manufacturer. Unfortunately, this does not prevent all type of other attacks, especially if the flash can still be accessed through scan microscope and altered with different ways that circumvent the write protection. And in some on some devices, this is we know it is a reality. Maybe not on the most modern ones. So our suggested alternatives usually include the Trust Anchor Store implemented through a secure element, which is usually designed for storing keys without any possibility to alter them from an external attacker, even if they have physical access to it. One-time programmable memory, which is actually designed for this purpose. So a lot of embedded systems, a lot of embedded devices offer an OTP area, and that's exactly what we need. So if it's impossible for anyone to modify an area of memory that's been written only once, that's a perfect use case for a Trust Anchor Store in this case. And of course, there are other solutions like out-of-band trusted providing authority. So someone who provides the keys in a read-only location on your device in the factory. And for instance, that could be your manufacturer with whom you have an agreement to pre-provision your keys on the device that they produce for you. How does it work then? You have this key pair, and you have wolfBoot that includes or can access the public key at runtime, and you have your development machine that's creating a signed firmware by starting from a firmware and a version number and the private key and using the key tool. At that point, it creates a new image as a blob that also contains manifest header. That's the authenticated firmware. At that point, wolfBoot will be able to authenticate that firmware and use it accordingly, either to stage it if it's already installed or to try and swap it when we talk about an update. Talking about update management, there are two possible strategies. Historically, let's say in literature for bootloaders, they both are supported by wolfBoot in two different contexts. There is an approach where the partitions are equivalent. They share the same memory, the same hierarchy level, and another one where the two partitions have two different roles based on their physical location. So the former case is ideal for position-independent firmware images, like on microprocessor-based systems where you can preload the image in memory, verify its copy in memory, and then stage it from a dynamic location. But it doesn't apply very well in the case of microcontrollers that need to execute in place. And in that case, we use the boot update approach, where the firmware always boots from the same physical location, and then the updates is stored on a separate partition. And in this case, of course, the advantage is that the update partition can be somewhere else because it doesn't need to be executed in place. So you can use almost the entirety of your internal flash to store the active firmware that needs to be staged. So wherever your non-volatile memory is used in execution in place mode and cannot be switched, of course, and where your microcontroller is expecting a physical location to start from as an entry point for your firmware address, the boot update approach will be used. Like for instance, if you have a single MCU with no external SPI flash devices, etc., this is a typical use case. So you have a very small partition at the beginning, which stores wolfBoot itself. Then you have a boot partition and update partition that is usually the same size, and they are basically occupying half of the remaining space in flash after you remove the bootloader partition and the swap partition. The boot partition is the partition where the current executing firmware is stored. So your current application or RTOS is stored there. And it needs to be still prepended with the manifest header, the original manifest header that's been added when the firmware was signed. So that wolfBoot can verify its authenticity and integrity at boot time. The update partition is the partition that receives the update, so it contains the candidate for the new update installation after the update has been received by the application, and then the two are swapped using this auxiliary swap partition, which is as small as a flash physical sector size, and it's used internally by wolfBoot to provide a reliable fallback mechanism. So if the power is interrupted during update, nothing is lost, and the update can resume from the same place, basically because we always keep two copies of the same sector during the update, thanks to this swap partition. In case of two partition on a CPU with virtual memory management and or a microcontroller that supports a hardware assisted memory swap, in that case you can swap the logical mapping of two physical partitions, so it is similar to the CPU case. So the bootloader can execute even from a different storage. It could be on a different ROM chip, for instance. Then you have two partitions. Each one contains a copy of the executing, for instance, Linux kernel image that you want to verify. And it can be two different copies. And so there is an election algorithm that runs at startup to check which image among those who check out their authenticity checks, which one has a greater version. And at that point, wolfBoot verifies the signature and stages the image from RAM. A copy of the existing image of the previously running image is kept after the update until a successful boot is confirmed, so that we can swap back by selecting in the elections process the image, the fallback image, if a failure was reported by the application itself. So what's the difference between these two cases? In microcontroller devices, typically you have the three partition mechanism with boot, update, and swap. Boot must be on execution in place. Update and swap can also be somewhere else. And if your platform supports hardware assisted swap, then you just it's required to use boot and update, but both, of course, in that case, need to be on execution in place. And wolfBoot duplicates itself in that case. In a CPU-based system, you can use an A/B partition, election, and boot. So typically, you can separate the stages to initialize the system if it's required. You can chain load other bootloader in both cases. So there is flexibility on the type of setup that you can basically realize with wolfBoot without any modification to the code. As I was saying, all the swap operations in the execution in place microcontroller versions are fail-safe, so the power can be interrupted at the worst moment possible. And during the swap operation, wolfBoot will keep track of how many sectors have been already replaced, and it basically prevents from breaking a device just by removing the power while the update is being installed. These are the two images are swapping. We do support some unique features. One of those is, as I mentioned earlier, bootloader updates. So wolfBoot, it can jump to memory temporarily and handling signed self-updates to update itself. Of course, this operation is not fail-safe. We do provide easy key management provisioning because of those tools that we distribute together with the bootloader, but also because of the fact that those tools themselves support third-party key provisioning. So if you have an external signer, for instance, as a cloud service, you can include that in the loop. We have a full guide, for instance, which has been introduced in the latest version that describes how to do this with the Azure HSM Vault. We do support Delta updates, which means that instead of transferring an entire new version of the firmware, we can just prepare a signed binary patch between the existing firmware on the board and the new version, which is usually smaller in size and reduces transfer and update time. This mechanism has two levels of authentications. First, it checks the signature on the patch, and then after the patch is applied, it checks again the signature on the resulting image. And due to the fact that this is a two-way patch, you can always restore the older version if something goes wrong. We do have a unique mitigation for glitch attacks, and especially fault injections with the more complex fault injections attack that involve electromagnetic interferences that are capable on a lot of microcontrollers to skip a specific instruction. We have put some architecture-specific countermeasures that will detect any jump within the code that was not foreseen by the boot flow, which otherwise could even skip your authentication check, your public key check, and allow for an attacker to inject a non-authorized firmware on your device. I briefly mentioned earlier that besides the algorithms, the classic algorithms that we support for firmware authentication, such as ECC, RSA, ED25519, ED448, we also have support for two stateful hash-based signature schemes called LMS and XMSS, which are quantum computing resistant, and that's been standardized by the IETF already. And they started appearing in recommendation by both NIST and NSA, and they have been recently re-implemented from scratch to be included in wolfScript, and those are already both possible to select as authentication mechanism in wolfBoot. They have a very short public key, around 60 bytes for LMS and 68 for XMSS. Fast verification at runtime, small footprint for the entire implementation. The LMS implementation is even smaller than our smallest classic pre-quantum setup. And the only downside of this is usually the fact that they have large signatures. So instead of ECC, for instance, ECC256 having a signature of 64 bytes, we're talking here about a few kilobytes, depending on the three parameters that you used for defining LMS and XMSS. We do provide also the same tool for signing and key generation, also for these two protocols. And in addition to that, some extra tools to calculate the signature size and the required manifest header size modification for accommodating these kind of signatures in your setup. We do have integration with the other products that we distribute. For instance, TPM, wolfTPM. wolfTPM manages the interaction with the TPM 2.0 devices, and it has different ways to interact with the bootloader phases. It can be used as a root of trust, using a hash of a public key to be compared, stored in a non-volatile slot, which can be optionally locked with an additional authentication step. We could offload the verification operations to hardware accelerator inside the TPM. We do support MeasureBoot using PCR extensions that can be also pre-extended by hardware components in some platforms. This guarantees that the first phases of the boot are also being monitored. We can seal secrets. For instance, on x86, we use this to sealing password to encrypt or unlock a SATA disk. And the seal is based on an external sign policy, so you can always set an additional authentication step before being able to unlock, for instance, generated password which will in turn unlock the disk. Keto platform authentication lockout and parameter encryption is supported, so this avoids eavesdropping attacks on the channel that's used to communicate with the TPM chip itself. We introduced in the last few versions integration with TrustZone-M. So wolfBoot is no longer just a bootloader on a new Cortex-M 33, 23, 55, etc. 35 are wolfBoot can be used as a supervisor, if you want, of the two security domains that are allowed there. So you have two separate domains. wolfBoot will run in the secure domain and stage application on or real-time OS in the non-secure domain. And on top of that, will also provide optionally non-secure callable API to access the crypto functionalities that are implemented in the secure area, and also will not allow application to directly access, for instance, reading out secrets such as private keys or symmetric keys, but rather use them through an API, which is also a solid standard, PKCS 11, which we have chosen for the communication between the applications and this non-secure call supervisor that's built in wolfBoot in those cases. We have recently presented another webinar showing this mechanism on SM32H5, which also includes a demo, which is the test application that you can find in wolfBoot repository, which shows the complete update and the usage of those secure, non-secure context domain switching functionalities as well. As mentioned earlier, it is possible always to integrate with an existing chain of bootloaders. There are multiple ways of doing this, of course. Two ways we see this done much more often. For instance, on microprocessor based devices, we can usually we have an initial first stage bootloader which is immutable and provided by the manufacturer, and that one provides some kind of mechanism as a root of trust to authenticate the bootloader, or at least verify its integrity as an immutable component. And this would be a second stage bootloader, which is usually a role covered by wolfBoot. And on top of that, of course, there might be integration with the other stages down the chain of trust. So once other components have been authenticated, it can be directly staged after wolfBoot. And this sometimes means that U-boot could be a third stage bootloader that's been authenticated by wolfBoot and can be also upgraded using the same firmware update mechanism that we offer usually for operating systems. On a totally different scenario, for instance, the second example I'm proposing here reflects the scenario where a user or a customer already has an existing bootloader, probably inherited from a legacy class of devices that they want to reuse, which has no secure boot features. So when you want to give secure boot powers to such piece of software that you don't want to sacrifice because maybe you spent time and engineering into it, we do provide a solution that where wolfBoot is compiled in your existing bootloader as a library. So the original bootloader can use functions to validate firmware images just by calling the wolfBoot API function calls. And the other advantage of this approach is that you don't need to worry about having a set of tools developed to manage the signatures and the keys and the private key, etc., because you can use exactly the same tool as the standalone wolfBoot even when you're using wolfBoot compiled in as a library, because it uses the same manifest header basically, so the format where the information are stored is still the same. So those are two of the common integration, let's say, variants that we see when dealing with a more complex boot chain that is not just limited to one boot stage. We are proud to announce that our crypto engine has got FIPS 140-3 certification as of 15 days ago. Which means that we now can provide certified FIPS 140-3 certified modules that include our cryptography engine. And wolfBoot, of course, is a perfect example of that. So if you need a secure bootloader that needs to be FIPS 140-3 compliant, we can provide that thanks to the fact that our crypto engine is already passed the validation and received the certificate. So it's just a matter of integrating the desired FIPS compliant version of wolfcrypt inside wolfBoot to make it a certifiable module at that point. The same way, the fact that we have chosen from scratch to use a safety-oriented design and defensive type of coding gives us a number of advantages in a market of safety certification, safety certified software, which means that wolfBoot has proven itself to be very popular in those markets where you need to have a specific safety regulation. You need to comply with specific safety regulations that require an extensive, for instance, process documentation or validation of the single line of code, like in the DO178C case. Why do we claim that our bootloader is safety oriented? Because we don't allow any dynamic allocations. We don't use any interrupt management or any type of user interaction at boot stage to keep our attack surfaces as small as possible. And all the flows are predictable at compile time. And the architecture is based on finite state machines that are fully populated. And of course, we do provide small parsers as mandated by RFC 1919, which means that by default, it becomes pretty easy and rather inexpensive to reach the level of safety regulation certifications when integrating embedded systems on different verticals. So wolfBoot has been successfully certified for airborne systems, so both aerospace market. It's been certified as a subcomponent in several IEC 62304 medical devices, and it can be certified as ISO 26262 due to the extensive documentation that we have on both our process, traceability of requirements into specific code modules, design, testing, etc. So those are pretty significant advantages in the market of secure bootloaders nowadays. This, let's say, concludes the part about the bootloader itself. I want to spend a few more words about what problems we have solved so far with the bootloader itself and what needs to be addressed in the application space. So we do provide a secure and reliable update mechanism. We do have those key management tools that are very handy and they can be used for preparing those firmware updates. We can detect and discard invalid or corrupted firmware or forged or not authentic. We manage interaction with any hardware accelerator that is supported by wolfcrypt and or through other modules like wolfDPM or wolf on PKI-CS11. We manage both clear text and encrypted storage, and encryption can be also done end-to-end using the sign tool from one side, and wolfBoot will decrypt the received image at runtime. We do manage domain separation in trusted execution environments, such as the TrustZone-M case for Cortex-M in the ARMv8 family. What we don't do is we usually don't prevent firmware updates to be intercepted because, as we said, we are transport agnostic, so the bootloader doesn't have any design choice on how the firmware is transferred. And we also don't ensure that the only authorized device can receive the updates. This depends entirely on how you decide to transfer the image. But luckily, those two are problems that have been already solved by other components. Since okay, our limitation here is that the RFC 1919 mandates us not to have anything to do with the transport, and the transport can be really anything. We have customers that use UART, Bluetooth, TCP/IP. We do have target-specific example in wolfBoot, even using X modem, so you don't have to quit your terminal emulation program and just can send the file while talking to console. And once the image is transferred, wolfBoot will validate and consider for the installation or staging in the next boot. But for those unsolved problems like the confidentiality and the authenticity of the receiver of those updates, protocols like TLS are exactly designed for this. So, for instance, when you want to communicate with your infrastructure providing firmware updates, you might want to choose protocols such as that are based on TLS and most likely TLS 1.3 if you're starting a design today. And we do offer TLS 1.3 socket security to secure the connectivity of any devices. And those are also as agnostic and transport agnostic, because wolfSSL can be integrated with any transport. It doesn't need to be a TCP/IP stack in that case either. But the additional thing here is that encrypted and authenticated endpoint kind of scenario is provided in order for you to transfer your firmware update securely. So this gives a little bit of an overview of our entire environment, how it looks like, and it's an ecosystem which is centered on our wolfcrypt crypto library and the wolfSSL embedded TLS library, which can also, as I was mentioning, work on top of custom transport layers, not just the TCP/IP stack, to provide transfer over any kind of media. Because we know already the embedded market is very heterogeneous when it comes to data link layer kind of solution. So let's say that we provide this kind of flexibility. And of course, there are a few secure protocols that are most popular in the IoT. One over everyone is probably HTTPS. And of course, SSH and SFTP is still very popular. And message passing protocol, where MQTT is definitely the market leader there. Why are those popular? Because they're standard, they are easy to integrate, and they provide the best encryption and client authentication solution, which are based on IT standards, IT without the O, so real IT standards. SSH, why is popular? Because it's the choice of the UNIX administrators, right? So it's a standard protocol that can interact with a number of tools that are already designed to work with the same protocol, SSH 2.0. And we do have our own implementation. It's called wolfSSH. It's a library that provides both sides of a SSH communication, so both server side and client side. And it can support secure copy, which is almost deprecated nowadays, and most importantly, SFTP. SFTP is a modern day replacement of FTP, but instead of being over TLS, is being implemented over SSH. And this gives a number of advantages on an embedded device, even when you don't actually have an actual file system, you can map a virtual file as your destination, the update partition if you want, where you're going to receive your firmware update. If we're talking HTTP, HTTPS, we're talking about curl. Curl has been a very popular project in the open source world for decades, and we are able to provide commercial support on curl because its author and maintainer Daniel Stenberg is part of our engineering team, and we're also working on something that's called the tiny curl, which is a reduced set of features from libcurl that have been ported to a tiny embedded scenario like a microcontroller with a FreeRTOS, and it fits within 100 kilobytes, including the TLS side, and supports HTTPS. And that's very handy, for instance, if you want to access REST interface, for instance, from an embedded device to a cloud using the latest and greatest protocols and the library that's probably the most popular HTTPS client out there on any systems in production nowadays. We mentioned MQTT. MQTT, we do provide as well a tiny library, only the client side this time, which supports up to MQTT version 5.0, and it's coded after the standard distributed by Oasis, and its default is of course MQTT over TLS, so on port 883, which means that Wolf MQTT has a perfect integration with Wolf SSL, and out of the box you can connect straight to any cloud services or your infrastructure broker. And we also do support MQTT-SN over DTLS or UDP for sensor networks. So as a conclusion to this webinar, we've seen how secure boot and remote firmware updates are becoming some kind of a requirement, not just in the IoT universe nowadays, but in all kinds of the embedded devices. And they are the solution for the vulnerability management on the field to be as reactive as possible to that. wolfBoot helps you implement secure boot through public key authentication as mandated by the RFC, and provides as a robust, reliable update installation mechanism. Wolf SSL in general brings TLS security to the IoT world, and when we're talking IoT, we're talking about standard protocols again, so SSH, HTTPS, MQTT, 3 valid choices to communicate with your cloud services, and we do offer solutions for those for uploading secure firmware updates on the field on your tiniest device with just a minimal set of resources, and still optimize that to use the latest and greatest protocols in the IT world. So this concludes my presentation. Thank you very much. I see that there are already a few questions in the Q&A, so I'll let Emma lead the discussion on this.
Amazing. Thank you so much, Daniela. All right, so one of the first questions is any POC or paper in regards to the glitch mitigation?
We did publish a blog post about that, so you might be able to find it on our website. The thing I can say is that this vulnerability has been discovered, and the mitigation have been validated by an external partner that specializes in this kind of attacks. And it's a company called New AE, and it's based in Canada.
All right, the next question is, what is meant by secure vaults? Is this a trusted computing enclave storage like Intel SGX?
It's slightly less complicated than that. Intel SGX provides an actual separation between contexts. A secure vault is usually part of a secure element. So it can be within the chip itself or as an external device entirely. And it guarantees that you can, for instance, generate keys that will never leave the device and or store keys that that you can provision once. And they usually have some kind of advanced protection against physical tampering as well.
Awesome. Okay. Another question for ARM Cortex-M deployment, is wolfBoot deployed as a TA, or wolfBoot seats in parallels to TEE and can check the integrity of the TEE?
So basically, when wolfBoot is deployed on Cortex-M ARMv8 as a supervisor, it doesn't require any external software. So there is no need for TA to be running on the device. So the separation is completely managed by wolfBoot itself.
Perfect. And then do you support SEC P256K1?
Yes, this is among the supported curves, supported elliptic curves that we support, and I believe this is even the default choice for ECC 256.
Perfect. And then one last question for you. Can wolfBoot replace U-boot in an embedded Linux system, or should they run in separate stages?
Interesting. This could be either. That's in the sense that a lot of customers decide that U-boot has a too big of a attack surface because of the interaction with the outside world, sometimes TCP/IP communication. So sometimes those things are not acceptable for the level of security required by the project. So we, in that case, act as a replacement for U-boot, and we can stage straight into the next stage. So it could be embedded Linux, for instance. But we have also some cases where the customer care about the extra features provided by U-boot, and in that case, we usually authenticate U-boot and then we stage into U-boot to continue the boot chain and leave, for instance, interaction with U-boot itself for customizing the configuration or things like this.
Okay, we do actually have a few more questions that popped in here, so I'm going to keep
nice.
going.
Okay, cool.
What interfaces / drivers are available in wolfBoot for error/failure logging?
So yeah, I see the questions. By default, none. If you would compile with the explicit debug, we default to UART, but we do have a printf interface that can be redefined. For instance, we have a customers that are currently using that through an RTT channel to the debugger.
Okay.
That can be overridden. Sorry.
No, you're all good. And then does wolfBoot use TFM?
Again, the TFM is the manager for TrustZone, I think, on the Cortex-M, right? So yeah, so exactly. So it's the TrustZone administration tool that we don't need basically because we replace TFM in the stuff where we manage our non-secure call. And in fact, there's two approaches that are kind of similar. The difference basically is that TFM exposes a PSA kind of API to the application, which is not an established standard. We decided to provide PKCS 11. So for instance, an operating system like FreeRTOS needs to use a translation layer to translate PKCS 11 calls into PSA, while if you're using wolfBoot instead of TFM, you can access the crypto calls directly using PKCS 11. But functionally, it can be similar. Well, wolfBoot does a number of other things, like managing the boot phases and the updates as well. And it doesn't duplicate basically the crypto implementation that's used for those two things.
Perfect. Well, thank you, Daniela, for hosting an informative webinar. Thanks for everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blogs, and get the latest Wolf SSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions at all, don't hesitate to shoot us an email at facts@wolfssl.com. We're here to help. Thanks again, and we look forward to seeing you next week on July 31st for Medical Device Security, Key Strategies for Cybersecurity and Data Protection. Thank you, guys.